This time I will be discussing about the data structure tree. A tree is simply a type of data structure in which each element or node in the tree is attached to one or more elements or nodes directly beneath that node. The connection between elements or nodes are called branches or edges. Another definition for tree is it is a collection of elements or nodes, one node of which is distinguished as the root, along with a parenthood relation that places a hierarchical structure on the nodes or the elements. Common examples of data structure tree are first, file system. In a file system like the one in this figure, directories or folders are structured as a tree. So we have here the root folder, which is the parent folder of all folders, and we have under this parent folder, which is distinguished as the root folder, we have several folders under it, or we call this subfolders. So we have dev, etc., sbin, temp, users, usr, and var. Under the root folder, which is this, we have 7 subfolders. These are like children of the parent node, which is this one here. And say this one, this subfolder, have also 4 subfolders, which are cups, httpd, init.d, and postpx. These are the 4 subfolders of this folder. The parent folder is this time, and it has 1, 2, 3, 4 children folders or 4 subfolders. So the 4 subfolders are like 4 children of this parent node. And also here we have a parent node of these 3 subfolders. And this one also is a parent folder of these 3 subfolders. And this one, lastly, is the parent folder of these 3 subfolders. So this is like a parent folder or parent node of these 3 subfolders or children nodes. So in a data structure tree, one node is distinguished as the root. So being the root, there is this established parenthood relation among the nodes. Like in this case, among these nodes, this one is the parent node, and all of this are the children nodes or the children subfolders. And at this point here, this one is distinguished as the parent folder or the parent node, and these 4 nodes here are the 4 children nodes of this parent node. Now, in the definition, it says here that the connection between nodes or elements are called branches or edges. So all of these arrows here are branches or edges. So basically, a data structure tree consists of nodes and branches. Another word for that is edges. And among all of these nodes in the tree, one is distinguished as the root. Okay, so there is only one root and several children nodes in the hierarchy. Another common example we have is a family tree, like this figure here on the right side. A family tree is a tree structure of ancestors, grandparents, parents, children, grandchildren, and so on. So this is the root node, and child 1 and child 2 are pointers to the left child and the right child, the first child and the second child. And then this child node here of this parent node has 3 children. So these are node 3, node 4, and node 5. So child 1, child 2, child 3 here are pointers to these 3 nodes respectively. And on this side, for the second child of the root node, we have a pointer, child 1, pointing to this child node, node 6. And all these nodes here could also have children nodes. Okay, so this may have 0 or more children nodes. The definition of data structure tree is recursive. First, a single node by itself is a tree. So say for example, we have here node n. That single node is considered a tree. This node is also called the root of the tree. So this is a one node tree, and that one node is also called the root of the tree. Second, suppose n is a node and T1, T2 up to Tk are trees with roots n1, n2 up to nk. And say for example, for this tree T1, the root is n1, and say this has children nodes. Say this is n11, and another child node of n1 is n12, and then n12 has three children nodes. Say n121, and this is n122, and this is n123. And say this node here, the first node, n11, say this has two children nodes called n111, and the second child node is n112. And say the root of 3T2, which is n2, has two children nodes, n21 and n22, and say n22 has one child node, n221, and say this 3tk here with root nk has also children nodes, and say the first is nk1 and the second is nk2, and nk1 has two children nodes. Say this is nk11 and this is nk12. There are k trees, and these k trees are denoted as t1, t2 to tk, and t1 tree has root n1 and t2 tree has root n2, and 3tk has root nk. Now out of this one node and k trees, we can construct a new tree by making n to be the parent node of nodes n1, n2 up to nk to become children nodes of this single node n. So there will be a connection now from n to n1, n to n2, and n to nk. Now, as a result, we have constructed a new tree. And in this new tree, n is the root, and n1, n2 to nk are called, okay, these nodes here are called the children nodes of root node n, which is this. In this new tree, n is the root, and t1, which is this, that is your t1, and t2, which is this, and tk, which is this, are called subtrees. Okay, so t1, t2 up to tk, these are now called subtrees of the new tree, where in this new tree n is the root, and n1, n2 to nk are the children nodes of root n. Now we also have what we call an empty tree. An empty tree is denoted by this symbol in most books. Okay, so we call this an empty tree. And of course, an empty tree has no nodes. So in summary, a tree can be first empty, denoted by that symbol, meaning no nodes. Second, a tree can be one node only. That one node is also called the root of the tree. And number 3, a tree could be consisting of several nodes with parenthood relation among the nodes. We have here some terminologies we use to reference the data structure tree. First is root. As defined earlier, root is the topmost node, the only node without any incoming branch or edge. As you can see here in the figure, A is the root of this given tree. It is the topmost node and it is the only node without an incoming branch or edge. So there is no incoming branch or edge. It has only outgoing. Like in this case, we have 3 outgoing branches or edges. From A going to B, from A going to C, and from A going to D. We will come back to this later, what a proper ancestor is. Second is leaf. Leaf is a node without proper descendants. We will come back to that definition later. Leaf is a node without an outgoing branch or edge. So, which of these nodes here in the given tree are leaves? Again, a leaf node is a node without outgoing branch or edge. So, this node E has no outgoing. It has no outgoing branches or edge. So, this is a leaf. K is also a leaf because it has no outgoing branch or edge, or it's a node without children nodes. So L is also a leaf, M is also a leaf, N is also a leaf, and I is also a leaf, and J is also a leaf. So what is a leaf again? It is a node without outgoing branch or edges, or it is a node without children nodes. So if it has no outgoing branch or edge, it also follows that it has no children nodes, because from, say, given this node, you only have outgoing branches or edges when there are children nodes, like we have here N1, N2, N3. But if N1, N2, and N3 do not exist, if this do not exist, or if N has no children, then it has also no outgoing branches. So again, a leaf is a node without outgoing branch or edge, and therefore it is without children nodes. Basically, as mentioned before, a data structure tree consists of nodes and branches. And these nodes could be the root, a leaf, or it is an interior node. So again, could be the root. Second, it is a leaf, or it is an interior node. So if it's not the root, not a leaf, then it is an interior node. So in this given tree, we identified A to be the root of the tree. Okay, take note, the root. We say the root, we use the because it is the only one. There is no other root. There is only one root in one tree. So A is the root, and E, K, L, M, N, I, J are leaves. So what remains are the interior nodes. So what are the interior nodes here? These are B, C, D, F, G, H. So how many interior nodes do we have? 1, 2, 3, 4, 5, 6. So we have here as interior nodes in the given tree, nodes B, C, D, F, G, and H, while the leaves are E, K, L, M, N, I, and J. And the root, okay, it's only one, it is A. So again, a tree node is either the root, a leaf, or an interior node. So in this given tree, these are the classifications of the nodes. A is the root. It's only one because one tree has only one root, and the leaves are these nodes, and the interior nodes are these nodes. So a node is an interior node if it's not the root or it's not a leaf. Another term we have here is path. Path from node N1 to Nk is the sequence of nodes N1 to Nk, or this series of nodes from N1 to Nk, such that Ni is the parent of Ni plus 1 for I from 1 to k minus 1. Or we could define path as an ordered list of nodes that are connected by branches. Is there a path from A to I? Yes, there is. And what is this path? A, D, and I. So there is a path from A to I via D. So we call this a path from A to D, D to I. So this is the path from A to I. We could denote it similar to the notation of a line segment in mathematics. We say the path from AI, or in mathematics, that's the line segment between the point A to I. Or in data structure, this is from node A to node I. The path is denoted as such. And this path is the sequence of nodes from A to this node, from D to that node. It's a sequence when there is connecting paths from one node to the next node. So from A to D, there is a connecting branch, and from D to I, there is also connecting branch. So we say that this is a path because they are connected by these branches. Next is length of a path. What is length of a path? Length of a path is the number of branches or edges along that path. So the number of branches along the path. So for example, the path from A to I, which is the sequence of nodes from A to D and D to I, how many branches or edges are there along that path? From A to I, there are 1, 2 branches. So the length of this path AI is equal to 2 because there are 2 branches along the path going from A to I. The length of a path is also defined as 1 less than the number of nodes in the path. So from A to I, in the path AI, how many nodes are there? There are 3, right? A, D, and I. 3 minus 1, that's 2. So the length of path from A to I is 2. So you could define length of a path by the number of nodes in the path, and it is number of nodes minus 1. Or if you define it basing on the number of branches or edges along the path, it would be just the number of branches. Next term is children of a node. What is children of a node? It is the set of nodes having incoming edges from the same node, called the parent of the nodes. B, C, and D are called children of node A because they all have incoming edges from the same node A. B has incoming edge or branch from A. C has incoming edge or branch from A. D has also an incoming branch or edge from A. So again, nodes are called children nodes of the same or one node if they all have incoming edges or incoming branches from the same node. And that same node is called the parent node of these children nodes. Next term is parent node. What is parent node? A node is parent of all the nodes it connects to with outgoing edges. So the parent node of BCD is A because they all have, BCD all have the same source node from which their incoming branches are from. The parent node of E and F is B because these nodes E and F have the same source of their incoming branches. Next term is ancestor of a node. What is ancestor of a node? Ancestor of a node is defined as if there is a path from node A to node B, then A is an ancestor of B. So again, an ancestor of a node is defined as when there exists a path from node A to node B, or from the first node to the second node, then the first node is an ancestor of the second node. Next is descendant of a node. If there is a path from node A to node B, then B is a descendant of node A. What is proper ancestor of a node? It is an ancestor of a node other than the node itself. So this simply means that a node is its own ancestor, and from the next definition of proper descendant of a node, it is defined as descendant of a node other than the node itself. So take note from these two terms, proper ancestor of a node and proper descendant of a node, it follows that a node is its own ancestor and descendant. So for example, if you're going to find out the ancestors of node F, what are the ancestors of node F? These are the ancestors of node F. So from F, B, and A. Okay? So from itself, you go up, follow the path from itself, going to the root, and all the nodes that you pass by, all the nodes in that path, those are the ancestor nodes of the node. This is F. From itself, you list that node F as its own ancestor, and then you go up to the root. So all the nodes in this path are ancestors of F. So F included, you have there F, and then B, and then next is A. So again, a node is its own ancestor and descendant. So if you're going to get also the descendants of node F, you're going to follow all the paths from node F downwards to a leaf. So from F going to a leaf, you have these two paths, and all the nodes therein are from F itself, K, and L. Okay, so these are the descendants of node F. So again, a node is its own ancestor and descendant. So like this one, ancestors of node F, F is included as its own ancestor, and then going up to the root, you have B and A. And for the descendants of node F, from itself as its own descendant, you go down to all the leaves. So from F, following this path, you reached a leaf. So all the nodes therein are FK. So you have FK. And following this path, going to a leaf, ending in a leaf, you have F and L. So you have F and L. So it's the union of all the nodes that you can reach following all the paths from that node downwards going to a leaf. And so if these are the ancestors of node F, what are the proper ancestors of F? Proper ancestor of a node F, from the definition, it's an ancestor of a node other than the node itself. So other than the node itself, you just remove this from that list of ancestors. You have only B and A. So these are the proper ancestors of node F. But For the ancestors of node F, F is included. And so for the proper descendants of node F, what are the proper descendants of node F? The proper descendants of node F is the set. Looking at the list of descendants, you have F, K, and L. And for the proper descendants of F, the definition says it is a descendant of a node other than the node itself. So you remove the node itself from the list of descendants. That makes it the proper descendants of node F. If you remove F, you only have K and L. So this set of nodes K and L is the set of proper descendants of node F. So the proper descendants of node F are K and L. The next term is subtree of a tree. What is a subtree of a tree? It is a node together with all its descendants. So if you cut this, you have E separated from the original node. So this is called a subtree of the original tree. If you cut this, that results to a subtree D, I, J, and we call this a subtree of the original tree. So a subtree of a tree is a node together with all its descendants. So this is the node together with all the descendants, which is this one, resulting to that one. So if you cut this, we have a subtree, which is this. So this is a node together with all its descendants. So now you have a subtree C, G, H, M, N. So this is a subtree of the original tree. So again, a subtree of a tree is a node together with all its descendants. Next is height of a node. The height of a node in the tree is the length of the longest path from the node to a leaf. So when you try to get the height of a node, you're going to find the longest path from the node down to a leaf. So if we're going to find the height of node C, what is the height of node C? You find the longest path from the node C to a leaf. So from node C to a leaf, this is one path. Okay. And another path is from the node C to a leaf is this one. From the node C to a leaf, M. So that's another path. And the third path is from node C to leaf N. So since from node C going to a leaf, there are 3 leaves that you can reach from node C, and these are leaf G, leaf M, and leaf N. And so there are 3 paths also, okay, from C to each of the leaf. So the paths are CG, the second path is CHM, and the third path is CHN. Now, among these 3 paths, okay, first path, second path, third path, from node C to a leaf, GMN, which is the longest? C to G, the length of that is 1. C to M, the length is 2. C to N, the length is 2. So the longest path is either of these 2 paths. Okay? So the length of the longest path from node C to a leaf, M or N, is 2. And therefore, the height of node C is 2. Next term we have here is height of a tree. The height of a tree is the height of its root. So, what is the height now of the given tree? Whose root is node A? What is the height? The height of this whole tree is the height of the root A. So, what is the height of root A? You have to find the longest path from root A to a leaf and then get the length of that longest path. That is now the height of the whole tree whose root is A. So what are the paths from root A to a leaf? We have A to K, this path A to K. A to L is going to A, B, F, and then L, this path. And then M, A to M is from A to C to H to M. That's the path. And then the last one is A to N. A to N is from A, C, H, and N. Okay, so there are 4 paths with the same length. And what is this length? Okay, so all of this the same. And the length is 1, 2, 3. To K. To L, it is 1, 2, 3. To M, 1, 2, 3. And to N, 1, 2, and 3. So all these 4 paths are equal to length 3. And this is the longest. We have here from A to E, this is a leaf, but the length is only 2. We have another one from A, D to I is a leaf, the length is only 2. We have another one, and this is the last one, from A to D to J, this is a leaf, the length is 2. So the longest is 3. And therefore, the height of this given tree, whose root is node A, is equal to 3. Next term we have here is depth of a node. What is depth of a node? It is the length of the unique path, take note, unique path, from the node up to the root. So take note that when you're going to get the height of a node or the tree, you are going to find the longest path going to a leaf. While if you're going to get the depth of a node, you're going to consider only one unique path. Okay, there is one unique path to consider, and that is from the node to the root. So when finding the depth of a node, you're going to take a look at the unique path from the node going to the root, while finding the height is finding the longest path going to a leaf. So from a node going down, that's determining the height. From the node going up to the root, that's determining the depth of a node. So what is the depth of node H? Node H is this node. Depth is length of the unique path from the node up to the root. So you don't have to get the longest path because there is only one path from the node going to the root. Okay? So what is the length of that unique path from node H to the root? That is 2, right? So the depth of node H is equal to 2. While the height of node H is what? The height of node H is finding the longest path. And there are only 2 paths going to a leaf from H. It's H to M and H to N. And these 2 paths are equal. They have length 1. So the height of node H is 1, while the depth of node H is 2. Say we're going to find the height of node E and the depth of node E. Height of node E from that node to a leaf, that is 0, and depth of node E is this path going to the root A, that is 2. Next term we have here is siblings. What is siblings? These are children nodes of the same parent node. So nodes in the tree that are children of the same parent are said to be siblings. So in this given tree, which are siblings? First, we have BCD, right? These three nodes, B, C, D, are siblings because they have the same parent node, and that is A. Another siblings are this node E and F. Another siblings would be G and H. Another sibling would be I and J. And K and L are siblings because they have the same parent node F. And lastly, M and N are siblings because they have the same parent node H. Now for these next two terms, ordered tree and unordered tree, take a look at these two given trees. We have here tree T1 and another tree T2. Say tree T1 has this hierarchy of nodes where A is the root and the children of A are B and C. This is the first and the second child, or the left child is B and the right child is C. And for node B, it has two children nodes. The first one is D and the second one is E. And on the right side, we have 3 T2, and it has the root A, and the children nodes are C and B, where C is the first and B is the second child of A. And for node B, the children are E and D respectively, and E is the first child and D is the second child. Case 1, if T1 and T2 are ordered trees. What is an ordered tree? It is a tree in which the order of the nodes is considered, or the order of the nodes matters, like a list of nodes, list of elements, right? If you have 1, 2, 3, and you have another list 2, 1, 3, these are not the same, right? Say this is L1 and this is L2. L1 is not the same as L2 because if these are list, the order of the elements matters. And the first element here is 1. In here, the first element is 2. So they are not the same. Okay? Because the order of the elements matters or is considered. But for sets, if S1 is 1, 2, 3, and S2 is 2, 1, 3, S1 is equal to S2 because for sets, the order of the elements does not matter or it's not considered. So as long as they have exactly the same elements, then they are the same sets. But for list, it's not that way. It's not L1 is not the same as L2. So the same principle applies to trees. Case 1, if T1 and T2 are ordered trees, then the order of the nodes is considered or it matters. And so if we are going to check if they are equal, we would check starting from the root. Do they have the same root? Yes. For the root, do they have the same children? Starting from the first child here is B, the first child here is C. Okay? So since it is ordered trees, then T1 is not equal or not the same as T2. For case 2, that is if T1 and T2 are unordered trees, just like sets, this principle here, An ordered tree is what? A tree in which the order of the nodes is not considered. So it doesn't matter if they have the same first child, second child, as long as they have the same children, right? So checking for case 2, if these are equal or same unordered trees, we start with the root. A is the root here in T1. A is the root in T2. Let's check. For the children of root A for T1, 3T1 are B and C, while in here for root or node A, the children are CB. So it's the same. You have B here, you have B there, C and C. Okay? So the children here are BC, the children here are BC also. The order is not considered, so they are the same. And for this node B, the children are D and E. And for this node B here, the children are D and E also. So the order doesn't matter because they are not ordered trees. These two trees, T1 and T2, are unordered trees. And therefore, it doesn't matter if you have DE here and here ED, as long as they have the same children. And C has no child here, C has no child here. So that's the same. C has 0 children, C here has 0 children. And therefore, at each level, they are the same. And so we could say here, if T1 and T2 are unordered trees, then T1 is equal or the same as T2. Another term we have here is binary tree. What is a binary tree? It is defined as a tree whose nodes have either 0 or 2 children nodes. So take a look at this tree we have here, where the root is A, and the root node A has 2 children nodes, B and C has 2 children nodes, D and E. Now say if we denote this or call this tree T, my question is this a binary tree? The answer to that is, of course, yes, it is a binary tree. Why? Because each node has either 0 or 2 children nodes. Say for A, we have here 2 children nodes, B and C. So this has 2 children nodes. B has 0 children nodes. C has D and E children nodes, so 2 children nodes. D has 0 and E has 0 children. So as you can see, each node in the tree has either 0 or 2 children nodes, which is of course true in this case. Therefore, we say that this is a binary tree. Now, there are some other varieties of binary tree which we're going to talk about later. And lastly, we have here the term mathematical tree or arithmetic expression tree. What is this? It is simply a binary tree that represents a mathematical or arithmetic expression. Say, for example, we have a mathematical or arithmetic expression A plus B. This mathematical expression is represented by this mathematical tree or arithmetic expression tree, where the operator is the parent of the two operands, which are A and B. Okay? So this is left operand, this is right operand, and plus is the operator. So if we are going to draw the mathematical tree or arithmetic expression tree to represent this mathematical expression or arithmetic expression, then it would be this one here, where the operator is the parent node of the two operands, where you place the left operand as left child and you place the right operand as the right child of the operator. Now, if we have this A plus B times C, what is the mathematical tree or arithmetic expression tree to represent this expression? Now, take note, there are now two operators, the plus and the multiplication. Since this is infix, this follows the MDAS rule. So this is performed first and this one is performed second. So performing this one first, we draw this sub 3. Because this is sub-expression, we call this sub 3. So that is multiplication and the left operand is B and the right operand is C. And this sub-expression is the right operand of plus, okay? And A is the left operand of the operator addition, okay? So, since this sub 3 represents this sub-expression B times C, which is the right operand of addition, then this whole sub 3 here is the right operand of the operator plus, and A is the left, so we draw A here. So this is now the mathematical tree or arithmetic expression tree representing the mathematical expression A plus B times C. Say we have here another example. 4 plus 9 divided by 3 minus 2 times 6. What is the mathematical tree or the arithmetic expression tree to represent this expression? So this is infix, so we follow the MDAS rule. This is performed first, and then this is second, and then this one is third, and then this one is fourth. This sub-expression, 9 divided by 3, is represented by this sub 3, 9 divided by 3. Okay, so 9 divided by 3, that is the sub 3 representing this sub-expression. And then we have here 4 plus this one. So this is the right operand and the left operand of the plus, right? So this would be plus in here, and the left operand of plus is 4. So 4 plus the sub-expression is represented by this sub 3, 9 divided by 3. And then this, the whole result, 4 plus that one, the whole value of that is the left operand of minus, and the right operand of minus is this sub-expression, right? So it would be minus is there on top, and the right operand of minus is this one. Okay, this has value already because multiplication is performed first. So this value 2 times 6 is the right operand of minus. So it would be this one times, and that is 2, and this is 6. Okay, so the resulting mathematical tree or arithmetic expression tree that represents the mathematical expression which is given here is this 3. Now, what have you noticed to the order of the operators in the tree? Remember, this is infix form, which means that it follows the MDAS rule. Multiplication and division are performed first before addition and subtraction, right? And so, as you see in the tree, multiplication and division, which are performed first, appear in the lower part of the tree. How about addition and subtraction? Where can you find these operators in the mathematical tree? Notice that they appear on the upper part, right? So, addition and subtraction, which are performed later compared to multiplication and division, appears in the upper portion or part of the tree. So what does it tells us as to the order of precedence of the operators? It tells us that the operators which are performed first or earlier appears on the lower part of the tree, while those operators such as addition and subtraction which are performed last appears on the upper portion or part of the tree. So it follows that the higher the order of precedence of the operator, the lower it appears in the mathematical expression tree. Okay, so that is our conclusion. Again, the conclusion is the higher the order of precedence of the operator, the lower it appears in the mathematical expression tree. And if you try to look at again the mathematical tree, what is the root? The root node is subtraction. Why do you think subtraction is the root of this mathematical expression tree? From the principle of order of precedence of the operators, again, remember that those operators which are performed last appear on the upper part of the tree. So the root node of the mathematical tree is the operator in the expression which is performed last. So the operator that is performed last in the mathematical expression, that becomes the root node of the mathematical expression tree.